ערב טוב, צהריים טובים, אחר צהריים טובים, ערב טוב. זה אירוע שהוא בעל אופי משפחתי. כל אלה שהם חדשים כאן שידעו שזה משפחת אדמס המורחבת. גם בני המשפחה באים פה וגם מלגאים משנים קודמות. והחדשים אולי סבורים שהאקדמיה וכו' וכו', אבל זה באמת אירוע בעל אופי משפחתי. ואני שמח קודם כל לארח את כל הנוכחים. אנחנו פה, במסגרת הזאת, זה מין אירוע משולב. מרסל אדמס, בן 94, אני אעבור לחלק באנגלית, כשנצטרך יהיה לברך אותו. חוגג יום הולדתו ה-94, והיה אירוע משפחתי לדינה, אני מחפש את דינה. היא יצאה. בסדר, הייתה בת מצווה במשפחה. והחיבור, האמת היא, בין מרסל לבין האקדמיה, הוא כזה, קיבלנו כספים מתורמים שונים במהלך הפעילות של האקדמיה. מעולם לא היה לנו קשר אישי אמיתי ומשפחתי משולב עם משפחת אדמס במובן הרחב. לינדה וגיל גרים בארץ, הילדים גדלים כאן. הפעם הראשונה שפגשתי את גיל הם היו עדיין קנדים, אז מאז קרו הרבה דברים. אנחנו היום 95 פלוס של מלגאי אדמס. זה בהחלט החלום שלו האישי. הוא לא רצה, הוא רצה שינתנו מלגות בתחום המדעים לדוקטורנטים. הוא לא רצה לשמוע מדעי הרוח ומדעי החברה, ורק למדעים, והוא רצה לסגור חוב אישי. חלק מכם מכיר את הסיפור, לא אחזור עליו היום, שלא, על זה שב-51 הוא עבר לקנדה. והחלק הזה, האמת היא, זה חלום אישי שלו. אני מקווה שהחמימות שהקבוצה נותנת לו, זה בהחלט ההחזר האישי לכל הפעולה. כפי שאתם רואים, כל הפעילות נעשית בצורה הצנועה ביותר, האמיתית ביותר. אין את כל החגיגות והצרמוניות שמקובל במקומות אחרים, זה אמיתי. הפעילות הולכת למדעים והולכת אליכם. ואנחנו שמחים לארח אתכם, זה כבר קבוצה של 100, כמעט 100 fellows, זה בהחלט בעל אימפקט על מערכת המדע, סתם סדרי גודל. בכל המערכת ההשכלה הגבוהה בטניור טראק יש היום 4,200 חברי סגל. מישהו תורם, ויש כבר 100 כאלה שהם יכול להיות בפוטנציאל טניור טראק, אז זה בהחלט בעל משמעות, והוא בהחלט עשה את זה. אז אני אעבור לחלק האנגלי. מרסל, I'm turning now to English. The Israel Academy of Science and Humanities congratulates Mr. Marcel Adams on the occasion of his 94th birthday and expresses its great appreciation for his fruitful efforts to promote excellence in science in Israel. I'm very happy to welcome Mr. Marcel Adams and his family, Linda, Gil, Leah, Yoni, Aviv, Dina, והחלק הישראלי, רותי ברנור, רוברט אבן, מגני תקווה, אני יודע, ואדריאנה קוטלר. אני מקווה שלא שכחתי מישהו מהמשפחה, אבל אלה השמות שנמסרו לי של נוכחות ברגע זה. I'm also pleased to welcome to the family the new Adams Fellows for the 2014, with of course all the senior fellows who came to the seminar, to this workshop. I would like to thank Professor Ruth Arnon and Professor Dan Shechtman, who is going to talk about quasi-periodic materials, paradigm shift in crystallography. אני רוצה להודות למוטי סגב שנמצא פה, שהוא גם חבר אקדמיה וגם פרופסור מחקר בטכניון. תודה באמת על הנוכחות. I wish to thank the committee members headed by Professor Amiram Greenwald for the selection of the new members, Adams Fellows. And I just want to repeat, for us, roughly about 100 Adams Fellows is a seminal contribution to science, and it has an impact on the scientific community in Israel. תודה רבה. ועכשיו פרופסור רות ארנון, נשיאת האקדמיה, תברך.
כיוון שזאת האקדמיה הישראלית הלאומית למדעים, אז אני אדבר בעברית. אני מבינה שרוב המשפחה מבין עברית. באמת לעונג ולכבוד לי לברך את מרסל בעיקר, לכבוד יום ההולדת ה-94 שלו, ואנחנו מחכים שאתה תהיה פה גם בשנה הבאה, ותכף אני אגיד למה. ולפתוח פה את האירוע, יש שני אירועים בשנה שהם קשורים למלגאי אדמס, האחד מהם זה טקס אדמס, והשני זה סמינר אדמס שבו מתקיימת ההרצאה. חוץ מאיזה אירוע שנתי של טיול וכדומה, שאתם ודאי תיוודעו לו במשך השנה. התודה שלנו למרסל היא כפולה ומכופלת, אנחנו מודים לו על זה שהוא אפשר לאקדמיה לקחת חלק בתמיכה ובעידוד של דוקטורנטים מצטיינים בארץ בתחום המדעים, ועד עכשיו, התוכנית התחילה לפני כ10 שנים, ועד עכשיו, עד השנה הזאת, 87 מלגאים קיבלו את זאת אומרת, דוקטורנטים קיבלו את המלגה, אחד מהם נמצא איתנו פה כיום, ובשנה שעברה סטודנט שלו גם כן קיבל את המלגה, ככה שאנחנו ממשיכים את המסורת. השנה מקבלים 8 מלגאים נוספים שנמצאים כאן היום, יחד זה 95, בדיוק מתאים לכך שאנחנו נכבד בשנה הבאה את מרסל אדמס, כלומר יום הולדת ה-94 פלוס 1 לשנה הבאה, כמו שנוהגים עם הנרות. במסגרת התוכנית הזאת של מלגאי אדמס, המלגאים מקבלים לא רק את המלגה עצמה, שדרך אגב אנחנו הגדלנו אותה בשנה שעברה, א' כדי להתגבר על הנושא, כי המלגה נקובה בדולרים, ולכן כדי להתגבר על הפרש של שערי מטבע, וגם כדי להיות יותר אטרקטיביים, אבל מעבר למלגה עצמה, כל מלגאי אדמס מקבל גם, עומד לרשותו סכום של $3,000 להשתלמות, וההשתלמות יכולה להיות או נסיעה לכנס, או נסיעה לחפש משרת פוסט דוקטורט לקראת סיום הדוקטורט, או כל פעילות מדעית אחרת שבה הוא או היא נוטלים חלק באופן פעיל. אני חושבת שבאמצעות הדברים האלה המלגה היא מאוד אטרקטיבית. אנחנו שמחים על כך שהמלגה גם מושכת אליה דוקטורנטים מצטיינים במיוחד. בשנה שעברה החברה הישראלית לכימיה העניקה 6 פרסים, 4 מתוך 6 הזוכים היו מלגאי אדמס. ואני חושבת שזאת תעודת כבוד גדולה מאוד לכל התוכנית של מלגות אדמס בארץ, ואני מודה מאוד למרסל ולכל המשפחה על זה שאתם מאפשרים גם למדע הישראלי וגם לאקדמיה הישראלית לקחת חלק בפעילות ברוכה זו. וכל מה שנותר לי זה רק לברך אותך מרסל. אני יודעת שאתה מבין עברית, אז לכן אני... But I'll say it in English. All that I have want to say is to wish you again good health and to congratulate you and to bless you on your really beneficial activity for the Academy. And we hope to see you for many years to come, every year for the Adams Seminar that is celebrated on your birthday, to celebrate your birthday. ועכשיו אני מתכבדת להזמין את פרופסור דן שכטמן, שבאמת בזמן שהוא היה עסוק בצורה בלתי רגילה, בכל זאת הסכים לקחת על עצמו את המחויבות לשאת את ההרצאה בסמינר אדמס. ודני, אני באמת מודה לך על כך ממש מקרב לב, מודה ומעריכה. וההרצאה, נושא ההרצאה הוא כמובן על קוואזי כבישים, טייטל המדויק הוא Quasi Periodic Materials, a Paradigm Shift in Crystallography.
Mr. Adams, family, Uti Arnon, President of the Academy, winners, professors, guests, I'm very pleased to give this talk here. I've spoken from this stage a few times in the past. This time it's going to be a talk about the discovery of quasi-periodic materials, and I coined it quasi-periodic materials, a paradigm shift in crystallography. These are my affiliations. So in the mid-80s, there were 3 surprising discoveries on the structure of matter and its properties. And they came year after year, starting in 1994, and all 3 of them received the Nobel Prize. The first in line was the discovery of quasi-periodic material, 1984, faint red laser. My name, Ilan Blech, Denis Gratias, and John Kahn are on the first paper published. Second came the discovery of fullerenes, 1985. And third came the discovery of high-temperature superconductivity. Now, when high-temperature superconductivity was discovered, everybody was happy. Of course, superconductivity was discovered in 1909. But very few expected high-temperature superconductivity. So when this was discovered, everybody was happy. Now you could have superconductivity at liquid nitrogen temperatures and not at liquid helium temperatures, which is maybe useful. When fullerenes were discovered, also everybody was happy. Because here is another way in which carbon atoms can form balls with icosahedral symmetry, like footballs. There was some objection to the model, but they died very quickly. But when quasi-periodic materials were announced, and before when they were discovered, they met a lot of opposition. Vehement opposition. And I will talk about it shortly. Now, in order for you to understand a little bit about crystallography, for those who are not crystallographers, I will say a few words about order in crystals, periodicity in crystals, and rotational symmetry in crystals. Let's start with order. Here we have a drawing of a 2-dimensional lattice of atoms, and clearly you see that there is order here. What it means for you is that if I ask you to continue this drawing in this direction or any other direction, you know how to do it. Very simple, because there is order and you understand the order. That's all you need to know about order. Now, this lattice is not only ordered, it is also periodic. It means that the distance between every 2 atoms is the same. This distance equals this, and so on. This is periodicity. And because the lattice is periodic, there is periodicity in every direction. For instance, take this direction, and you see that there is periodicity there. Take this direction, there is periodicity there. Take this direction, periodicity there. Every direction, there is periodicity. Now, here is an example of periodicity. Let's go back for a second. Here, every motif is 1 atom. But that is not necessarily so. Sometimes the motif can be a molecule. Sometimes it can be a huge molecule. Here is an example of a 1-dimensional lattice in which the motif is not just 1 bar. You see that the bars are not equal in size. There are small ones and tiny ones and large ones. So what is the repeating motif? Here it is. You see? These large, large, small, small, large, large, tiny, small, large, large. This is the motif. And it repeats itself again and again, time and again. So this is periodicity of a larger motif in 1 dimension along a line. Again, periodicity. Sometimes, this example of the ribosome, for which Adayonat received the Nobel Prize, the ribosome is a very, very complex molecule. It's a huge protein. And in order to study the exact position of every atom in this huge molecule, you needed to create a crystal based on this motif. And Adayonat took many years to prepare the first sample. But once she had the sample of a crystal made of ribosomes, this was the beginning of the solution. And after she completed her mission to discover the position of each and every atom in the molecule and the function of the molecule, how it works, she received the Nobel Prize. So here's what she did. She created a crystal made of molecules which are huge molecules. Okay. Let's say a word about rotational symmetry. Here I have again the 2-dimensional lattice, and I have a little red handle so that you see what happens when I rotate it. I can rotate it 90 degrees, and it looks the same. 180 degrees look the same. 270 degrees look the same. And 360 degrees look the same. You can do it 4 times. This is why this two-dimensional lattice has a 4-fold rotational symmetry. This is rotational symmetry. Here are examples. Let's say a word about crystallography. The science of crystallography started in 1912. This is 102 years ago, with the famous experiment by a German scientist, von Laue, who performed the first X-ray diffraction experiment. And he proved in that experiment 2 major things. Number 1, he proved that crystals, as they imagined before, are indeed ordered. And he proved that X-rays have a wavy nature. This experiment marked the beginning of the science of crystallography. Now, crystallography is ancient. People imagined what happened in the crystal. People found crystals in nature or grew them in the laboratory, and the crystals had facets. And people measured the angles between the facets and came to conclusions that were correct, that crystals are made of atoms which are ordered. It was true, but they could not prove it. Von Laue provided a tool, and that tool was X-ray diffraction. A year later, the Bragg, father and the son, from Leeds in England, created the Bragg equation, and from there on, voila, we had a science of crystallography. And the people who did that science called themselves X-ray crystallographers. We are not as those ancient crystallographers who didn't have a tool. We are X-ray crystallographers. We have a precision tool to measure crystals. That was wonderful, but then it became an obstacle, as you will see. X-ray crystallography was the name of the science, and the tool of choice was X-ray diffraction. So this is the beginning of crystallography, and then based on the observation of von Laue, and based on hundreds of thousands of studies of crystals that were done between 1912 and 1982, for a period of 70 years, there was something common to all crystals. Number 1, they were ordered, and therefore crystals. The atomic order was there, and all of them were periodic. All hundreds of thousands, about 200,000 crystals, different crystals studied, they were all ordered and periodic. And so, based on these observations, multiple observations, this was the definition of a crystal. This is from a book by Quality, X-ray diffraction, and it says the following. A crystal is a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This was the definition of a crystal. This is the foundation of the science of crystallography. Hey, crystallographers, what do you study? We study crystals. What are crystals? Crystal is a material in which the atoms are ordered and periodic. Bravo. Life was simple, and the science of crystallography was a mature science. Mature science is a science in which people believe that they know everything about the science. Yes, you can discover new crystals, but the structures are known, and nothing shocking could be expected. Here is another definition, same meaning, different words. Atoms in a crystal are arranged in a pattern that repeats itself in 3 dimensions throughout the interior of the crystal. Now, crystallography in 1982 is judged, I know you cannot read it, by a book by Charles Kittel, Introduction to Solid-State Physics. This is the book that we studied when we were students. And something is marked in green here. And because you cannot see it, I have enlarged it for you. And now you can. And it says the following, the marked in green. We can make a crystal for molecules which individually, each molecule, can have a 5-fold rotation axis, like the ribosome, which is so complex. But we should not expect the lattice to have 5-fold rotation axis. Each molecule, whatever rotation axis you want. But the lattice, no 5-fold rotation. Why so? To understand why, well, before that, here is an example of a structure. This is, by the way, diamond. In high-resolution electron microscopy, each white spot is an atom. This is a carbon atom, and this is the order of atoms in a diamond. And as you can see, there is periodicity here. There is periodicity in this direction, periodicity in this direction, periodicity in this direction, any direction that you choose, periodicity. The order of carbon atoms in diamond is periodic. The allowed rotational symmetry is 1, 2, 3, 4, and 6. 5-fold rotation symmetry, as well as any other symmetry beyond 6, is forbidden in periodic structure. This is true mathematically. You don't need, there's a way to prove it, and I will show you one way to prove it, but these were the basic rules of crystallography. Now, let me take you now to away from the real space. The real space is where the atoms exist. The real space is where we exist. Well, most of us exist in real space. And this is the reciprocal space. This is another space, a mathematical space, which we call the reciprocal space. And this is the diffraction pattern, not taken by X-rays, but taken by an electron microscope. I will explain very briefly what we do with an electron microscope. We have an electron microscope is a huge machine. You sit at the machine. Nowadays, you don't have to sit by the machine. In modern microscope, you can sit in Kamchatka and do electron microscopy in Haifa, because everything is done by computer. But in an electron microscope, you shine an electron beam onto a specimen. Let's say that this is a specimen. It's very small. It's much smaller than this, 3 millimeters inside. And you shine this is a laser beam. You shine an electron beam in vacuum. And what happens is the following. This thing has a solo itself. You touch it, it's on. Excuse me for 1 second, I just want to turn it off. Shut up. Okay. So let's say that this is the specimen. So what happens is the following. We make the specimen very, very thin, so much so that the electron beam goes through it and hits a phosphorus screen on which you see the image. Phosphorus is a material that turns the energy of an electron to a lower energy that you can see with eyes. Short wavelengths becomes larger wavelengths. Well, anyway, this here is the transmitted beam that goes through. All the other beams are diffracted beam, based on the laws of the Bragg father and the son. So this is electron microscopy, and this is the reciprocal space. And the reciprocal space is an imaginary mathematical space that helps us understand what we see in the diffraction pattern. And this is a cross-section through that space. Now, also in the reciprocal space, there is periodicity of the diffraction pattern, because this was taken from a periodic lattice. The rotation symmetries that are allowed are 1, 2, 3, 4, and 6. No 5-fold rotation symmetry and nothing beyond 6 are allowed. Periodicity here, periodicity here, periodicity here, anywhere periodicity. And then something very interesting happened. You see, in order to understand how important it is, I need to tell you something about the International Union of Crystallography. You see, when the science of crystallography started, a union was created by the crystallographers called the International Union of Crystallography. These are the body that governs this union is hardcore mathematical crystallographers. These are no-nonsense people. Everything has to be defined from the very basics. Hardcore mathematical crystallographers. And then in 1992, they came up with a new definition of a crystal. And this is an amazing definition. Why so? Because if you read it slowly, it's a poem. You remember? The old definition said a crystal is. This doesn't say a crystal is. No. It says by crystal we mean soft. any solid having an essentially discrete diffraction diagram. Essentially discrete diffraction diagram, soft. And by aperiodic crystal, we mean, listen to this, any crystal with three-dimensional lattice periodicity can be considered to be absent. Is this a definition that came from the International Union of Crystallography? Those hardcore mathematical crystallographers? What happened? What happened is the story of the discovery. Now, 1982 was the 70th birthday of crystallography. Remember in 1912, von Laue, he was anti-Nazi, by the way, this German guy. 1982 was 70 years birthday of crystallography, and this was the year quasi-periodic crystals were discovered. Now, in order to understand what happened in the day of the discovery, let me take you to my laboratory. I was on sabbatical at NBS, National Bureau of Standards. This is in Maryland, a little bit north of Washington, D.C. And I show you my logbook from that day. Now, this logbook, of course, was never intended to be seen by anybody but me. These are short notes that I made for myself. And when I give a talk to students, and I do that 100 times every year around the world, I tell them, lesson number 1, you make an experiment, write it down in a logbook. This is lesson number 1. Because maybe you'll remember your experiment for a week, but you'll never remember it a year later, let alone 35 years later. Okay? Write it down, page by page. What did you do? Successful, not successful, doesn't matter. Write it down. So this is my logbook. This is electron microscopy logbook. And look at how much information it has. First of all, it has the date, April 8, 1982. I was working on aluminum 25 weight % manganese. This alloy was rapidly solidified. What does it mean? You melt the material and you cool it very, very rapidly. You make a ribbon, very thin ribbon that cools very rapidly. And it was a part of a project, a very applied project, by the way. This is the electron microscope. This is the plate number, picture number 1720. SAD is selected area diffraction pattern. It's a diffraction pattern like the one I showed you before. Another one, and 38K is a picture of the real space with magnification 28,000 times, and 17,000 times, and 36,000 times. And then I look at this picture, number 1724. I look at it and I said, wow. That's interesting. Now, let me tell you something. In the past, when the old Greeks discovered something, like Mr. Archimedes, he jumped out of the bathtub shouting, Eureka! We don't do that anymore. We don't jump out of the bathtub. Usually, scientists do not have time to take baths. We take showers. And we don't jump out. We just say, that's odd, or that's interesting. That may be a discovery. So I look at this picture. I'll show you the picture. I'll tell you what's interesting. And then I said, what is the diffraction pattern? So I take a diffraction pattern, and I write down tenfold with 3 question marks. What's going on here? Remember? Nothing beyond 6 is allowed. And then I took many more pictures that afternoon. The whole thing was one afternoon of April 8, 1982, to find out what I have. All these experiments were to find out what I have. I'll tell you about it. So this was it. This was the discovery. Now, this is the plate that I said, that's interesting. So what is interesting in this plate? Let me explain. This is a crystal. See, right here, this is a single crystal of aluminum 25 weight % manganese. And here's another one and another one. But some crystals are pitch black. This and this and this and this and that and that. Now, when a crystal is pitch black in what we call bright field image, it means that the energy, almost all the energy, goes to the diffracting spots, and nothing penetrates through. What? I have never seen anything like this in my life, and I was a veteran electron microscopy. I was very experienced electron microscopist. What's happening here? So I said, well, let's look at the diffraction pattern taken from this crystal. I do that, and this is what I see. I look at this diffraction pattern, and I said, אין חיה כזאת. There ain't such animal. There is no such animal. How do you say? There ain't no such animal. Why? Well, because I look at the diffraction pattern and say, okay, what is the rotational symmetry? So I start to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, no, no. Impossible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I write tenfold. But that's not all. Look here. There is no periodicity here. You take the distance from here, let's say to here, multiply by 2, you get here. And there is nothing there. No periodicity. No integers. Irrational numbers came into play, and the ratio of this distance to this distance is very close to the Fibonacci number tau. Why do I say very close and not exactly? Because if you take a and divide by b, you cannot get an irrational number. So this is an irrational number. But this came from theory later on. Okay, so this is the ratio, and the ratio of distances, this distance divided by this, is the Fibonacci number tau, mal plus root 5 divided by 2, equals 1.618. It's an irrational number, endless number of digits behind it. Okay, very, very strange. So what do we have here? First of all, we have many more diffraction patterns. What does it mean? I can take the specimen, and I can tilt it to any position I want, and rotate it to any position I want, and get diffraction patterns from all these directions. So this is the 5-fold, 2-fold, 5-fold again, and these are the angles between them, and 5. By the way, it's not 10-fold, it's 5-fold, but I could not know on day one that this is the case, because I needed to perform another experiment for the scientists among you. It's called Kikuchi pattern. Doesn't matter. So 5, 3, 2, 5. And this set of diffraction pattern has icosahedral symmetry. I will explain what it is. This is why we call it the icosahedral phase. Okay, enough of that. 1982. 1984, I came back to the Technion with no solution to the question what I have. And there I met Ilan Blech. Ilan Blech was a professor in my department of material engineering at the time. And he was the first person who believed in what I was talking about. I'll tell you the ordeal later on. And he said, let me see if I can develop a model that will explain what you did, what you found. He developed a model. And we sent a paper for publication, the Shechtman-Blech paper, and we sent it to Journal of Applied Physics in September of 1984. At the time, that summer, I was again at NBS. That paper, that was, no, that paper, let's go back. That paper was rejected very, very quickly. Now, I want to tell you something for the young scientists among you. Those days, when you wanted to publish a paper, you had to type it, and scientists, most scientists could not type. We had a secretary to type our handwriting on the computer, and then we printed it, and we put it in an envelope, and wrote the address, and put a stamp on it, and send it to the publishers. And a few weeks later, 2 or 3 weeks later, I received another envelope with my paper inside with a letter from the editor of Journal of Applied Physics. Says, Dr. Shechtman, thank you so much for your contribution. However, we are not going to send it for review because we at the editorial board decided that it will not interest the community of physicists. Why don't you send it to a metallurgical journal? So I am a good boy, I am. I sent it to a metallurgical journal, and that journal is Metallurgical Transactions, and it was accepted and published. But it was published later in June of 1985. Very slow publication, as this journal does. In the meantime, I showed that paper that was rejected to my host, John Kahn. John Kahn was an eminent scientist. He's with us today, too. And he's 87 now. And right. And he's not active anymore. But he looked at the paper and said, Danny, this was all wrong. Why don't we do something else? Write a short paper without the Ilan-Blech model, just your findings from the first week that you work, and send it to a quick publication to PRL, Physical Review Letters. We did that. This is the paper. We added Denis Gratias. So the Shechtman Blech Khan, and Denis Gratias is a mathematical crystallographer from France. John was not a crystallographer. He needed somebody to confirm that what I did was correct. Denis Gratias came. He added his skills and knowledge of mathematical crystallography. We wrote a very short paper, and we sent it for publication. That was published very, very quickly, and it was received in October and published a month later, November 12, 1984. This day was the beginning of the science of crystallography, of the science of quasi-periodicity, I'm sorry. Okay. Now, this is story number one. A few facts. What is icosahedral symmetry? This is an icosahedron. This icosahedron, by the way, is made of wood. And a year ago, somebody came to my office and said, can I borrow it to show it to my student for 1 hour? And never came back. I don't have that anymore. I don't know who took it. I don't have it. Anyway, so this is an icosahedron, and it has 6 5-fold axes. What is the 5-fold axis? Look here. Put your eye here and look down to the center, and you will see that there is a 5-fold rotation symmetry. Put your eye here. Look at the center. 5-fold rotation symmetry. So these are the axes. And so on. So 5-fold, there are 6 of them, and 10 3-fold, and 15 2-fold. This is an icosahedron. You can better understand it by looking at football, and tonight we will look. Some of us will look at football, and what you see here is that football is made of pentagons as hexagons, and if you look at this pentagon, you see that it has 5-fold rotation symmetry, 1, 2, 3, 4, 5 from this position. If you look from here, you see that 2-fold, nicely 2-fold, nicely 3-fold. This is icosahedral symmetry. And I doubt that those champions in football know that they play with icosahedral symmetry. I don't think they do. Well, anyway, this is icosahedral symmetry. What is quasi-periodicity? What is this? To know what quasi-periodicity is, I must take you back to the 13th century to look at Mr. Fibonacci, Leonardo Fibonacci de Pisa. His friends called him Blockhead, but he was the greatest mathematician of his time, and probably 500 years later, he was still the greatest mathematician until Newton and that generation. This is him, a painting of him. And this is a picture of an actual statue that was erected in his memory in Pisa. Just behind the inclined tower of Pisa, there is a graveyard under a roof, and this statue is there. I'm not sure that he's buried there, but the statue is there. To understand quasi-periodicity, we have to understand something about Fibonacci's rabbits. Now, this is general education. Everybody must know about Fibonacci rabbits because this is general knowledge, regardless of what your profession is. So these are Fibonacci rabbits. What do we have here? Mr. Fibonacci, Leonardo said the following. Let's assume that we have a female rabbit in the first month, and she has a husband or a boyfriend. He comes to visit her, and she's pregnant. And in the second month, she gives birth to a little one. And in the third month, she gives birth to another little one. This little one matures and does not reproduce for 1 month. This one gives birth to a little one. This one matures, and this one gives birth to a little one. So this is the order, and now you understand the order. Let's look here. This one, in the next month, will give birth to a little one. This little one matures. This mother will give birth to a little one. This mother will give birth to a little one. This one will mature, and so on and so forth. You understand the order, and in principle, you can continue this list forever. And when you do that, so number one, you agree that there is order. You understand how to continue this list. There is order there. There's a mathematical order here. Now, you can continue this forever, and there are 2 very, very simple equations. Don't be scared. What this one says is that the number of rabbits in each month and the nth month equal the sum plus sum of number of rabbits in the 2 previous months. It means the following. 3 is 1 plus 2. 13 is 5 plus 8. 8 is 5 plus 3, and so on. You take 2 months, add them, and you get the next month. So this is this equation. This equation says the following. If you continue this forever, and you go to the last one, and divide the number of rabbits in the last one by the number of rabbits in the previous month, then you get the Fibonacci number tau. An is the last one. There's no last one. It's forever. You go, n goes to infinity. Divided by the previous one, you get the Fibonacci number tau. It's an irrational number, 1 plus root 5 divided by 2. And this is the number. So this is the Fibonacci. The Fibonacci series is, I'm sorry, it's ordered, but there is no periodicity. It's quasi-periodic. Look here, what does it mean there is no periodicity? There is no motif that repeats itself of any size periodically. No motif that repeats itself periodically of any size. Large, small, large, large, small. Ah, here it's again. Large, small, but it doesn't continue. Large, large, small, it doesn't continue. There is no motif of any size that repeats itself. It's quasi-periodicity, and I will not go to the equations. This is not this talk. Okay, so this is quasi-periodicity in 1 dimension, along a line. Do we have quasi-periodicity in 2 dimensions? Yes, of course. Penrose tiles. Roger Penrose is an eminent British scientist living in our time, and he designed the Penrose tiles, the famous Penrose tiles. And these are 2 tiles, 2 rhombi, 72 degrees and 32 degrees. If you join them together according to certain matching rules, they will form this. Okay? You can tile a plane, you can tile a floor. By these 2 tiles, you have to match them according to certain matching rules, not just any way you want, but according to matching rules. And then you can tile a plane with these tiles without gaps. What's interesting in this is that if you take a diffraction pattern from this, you'll get something similar to the diffraction pattern that I found in those quasi-periodic crystals. It has 5-fold rotation symmetry. This is Roger Penrose. The one who discovered, by the way, the diffraction pattern is Alan Mackay, another British scientist, a crystallographer, who did just that. He took a diffraction pattern of that and showed that it forms 5-fold rotation symmetry, sharp spots in the reciprocal space. Okay, so this was 2 dimensions. What about 3-dimensional quasi-periodicity? Is there anything which is quasi-periodic with 3 dimensions? Of course. These are quasi-periodic crystals. And here is an example of one of them. Beautiful 5-fold facets. And this is in the system magnesium, zinc, cerium, taken by one of my students on a scanning electron microscope. Okay, enough of that. And now to the story. When I started to talk to my colleagues at NBS about crystals with sharp diffraction spots with 5-fold rotation symmetry and other symmetries, they said, don't you know it's impossible? What do they teach you at the Technion? Don't you know that there are no 5-fold rotation symmetry crystals? I said, I know that, and but here it is, right here it is. He said, no, it must be twins. I did not show you the experiment. For the sake of time, I did not show the experiments, but what I suspected in day 1, that these are twinned crystals, and we'll not go into details. I checked, and I did electron microscopy. There were no twins there, no twins, no defects. It was a crystal with no defects, and yet it has 5-fold rotation symmetry. And I said, yeah, I know, but it's not twins. The reactions were mixed. John Kahn, my host, was positive, encouraging. He came to my office and said, Danny, this material is telling us something, and I challenge you to tell us what it is. This was encouraging. He did not help in the solution, but at least it was encouraging. I spent days trying to draw models. Nothing worked because I tried to draw periodic models. Crystals were periodic. The negative reaction was from my group leader. This was the other extreme, the negative extreme. He came to my office one day, smiling sheepishly, putting a book on my desk. A book of X-ray crystallography, saying, here, Dr. Shechtman, please read this book, and so you'll understand that such crystals cannot exist. And I said, you know, doctor, I will not mention his name. I know this book. I teach at the Technion. I don't need to read this book. I am telling you, my material is not in the book. Took the book back, came back a couple of days later and said, Dr. Shechtman, I ask you to leave my group. You are a disgrace to my group. I cannot have my name associated with you. And anything bad? Okay. I don't want my name associated with you. Please leave my group. So I left the group and found another group leader that adopted the scientific orphan, and everything went okay. But this was a very negative and almost arrogant reaction. And everything was in between, encouragement and this type of reaction. And if you, these were the years 1982, 1984, when I was alone, trying to convince people that what I have is real, and I could hardly convince anybody. And yet, I did not have a model to explain what I have. If you want to see how I felt during that period of time, it was something like that. So these were the first 2 years. Then came the years after the publication, between 1984 and 1987. What happened in 1987, I will explain. By now, we had a growing community of scientists who took my discovery and made it into a science. And there were hundreds of people working on quasi-periodic materials in all the scientific world, in all the countries that have science, real science in them. But the International Union of Crystallographers said, bring us X-ray diffraction patterns. We are, remember, X-ray crystallographers. We don't believe in that electron microscopy. We don't know. That's not a real tool. They were they were very wrong, of course, because electron microscopy is a fantastic crystallographic tool, especially nowadays. Amazing crystallography. But they wanted X-ray diffraction. We could not give them X-ray diffraction because our crystals were very small. Very, very small, 1 micron inside. And in order to have a diffraction pattern for one quasi-periodic crystal, you need a crystal to be about maybe 1/10 of a millimeter. That's good enough. We didn't have that. But in 1987, my colleagues in France and in Japan succeeded in growing large enough crystals for X-ray diffraction. And these were the X-ray diffraction that they sent it to me, and I showed these wonderful images. You see, this is Large diffraction pattern. 5-fold, 1, 2, 3, 4, 5, 3-fold, 2-fold. Wonderful picture. I showed this very slide in the meeting of the International Union of Crystallography in Perth, Australia, 1987. And when I showed this picture, part of a talk, the community said, okay, Danny, now you're talking. They formed a committee that redefined crystals and adopted quasi-periodic crystals into the community of crystals. Right? This was a paradigm shift in crystallography. This decision to form that committee and accept quasi-periodic materials into the realm of crystals was a major, major decision. Okay, so you think, the International Union of Crystallography, all the hardcore mathematical crystallographers, they accept quasi-periodicity. Who will object? Not so fast. Because then there was Professor Linus Pauling. Now, Professor Linus Pauling was arguably the greatest chemist of the 20th century, definitely in the United States. He was the forefather of the American Chemical Society. He had hundreds of thousands of scientists that followed him blindly because he was such a great scientist. But he was wrong. And it was not the first time that he was wrong. Linus Pauling was a wonderful person, wonderful scientist, but he was not humble. He thought he knew everything. Nobody does. He did not know. And he had let's say, a battle of in which he tried to convince the community that quasi-periodic materials do not exist, and whatever I see and my colleagues see, whatever we see, are just defected periodic crystals. These are twin crystals, he said. And I knew from day one that there were no twins there. But Linus Pauling did not understand electron microscopy. He was an X-ray crystallographer. He did not accept. And Linus Pauling was a very flamboyant speaker. I heard him several times. And I met him personally several times. In fact, I went to Palo Alto. He had a laboratory in Palo Alto. And I gave a talk like this for one person. One person. I gave him a talk for an hour. At the end of the hour, he said, Dr. Shechtman, I don't know how you do that. Meaning, I don't understand electron microscopy. And I said to him, Dr. Pauling, let me ask you a favor. If you ever agree with me, don't keep it a secret. Yeah. That argument that continues, and I was not alone. He argued with me, with the community, and with everybody else. And one of his famous sayings was, Danny Shechtman is talking nonsense. There are no quasi-periodic materials, just quasi-scientists. Not very nice, but he coined that. He was wrong. And the argument between us ended in 1994 because he passed away. And from there on, no arguments. I want to mention a few names that made seminal contributions. These are Roger Penrose tiles, Alan Mackay, the man who showed that they diffract, that Penrose tiles diffract, make sharp diffraction spots in the reciprocal space. I want to mention Ilan Blech, who wrote the first and the second paper with me, Denis Gratias and John Kahn, who wrote the second paper that was published first, and Dov Levine and Paul Steinhardt. Dov Levine is now a professor in physics at Technion. Paul Steinhardt is a professor in Princeton. They proposed the mathematical model based on three-dimensional Penrose tiles. Ilan Blech proposed a physical model. They proposed a mathematical model. And so these are the people that made the first seminal contribution. After that, there were many, many other contributions. I want to sum up by saying the following. While order was synonym to periodicity before, now we know that order can be periodic, it can be quasi-periodic, and it is open-ended. If somebody comes with a new discovery of another type of order in crystals, we listen. We don't say, go home. We listen. The International Union of Crystallography became more humble, and the humble scientist is a good scientist. Now, in order, I would like to finish, and I don't know if we have time for a question for you, but I make time to ask my question, and I will give you also the answer. And the question is, why is it that quasi-periodic materials were discovered only in 1982 and not before that? You see, there were 70 years of crystallography, 70 years of crystallography. Thousands upon thousands of eminent crystallographers studied 200,000 crystals or so, and nobody saw quasi-periodic materials? Why? Is it because they're very rare, and I stumbled upon one? Is it because they are not stable? Is it because they're difficult to make? Is it because they're made of rare elements, praseodymium, gadolinium, and a touch of uranium? What is it? Well, let's see. Are they rare? Not at all. There are hundreds of quasi-periodic materials. There are hundreds of quasi-periodic materials. Here's an example. This is partial list of quasi-periodic materials based on aluminum alone, and there are many based on other elements. There are hundreds of them. That's not the reason they were not discovered before. Are they not stable? Many are stable and transform to periodic structure at temperature. But quasi-periodic crystals are thermodynamically stable, and here are a few examples of thermodynamically stable ones. But also the ones that are not stable, what does it mean not stable? They transform into periodic crystals when you heat them up to 400 degrees C. But at room temperature, Okay, no problem. So this is not the reason that they were not discovered before me. Are they difficult to make? And I tinkered one of them. Not at all. They can be made by many manufacturing technologies. You can cast them, you can rapidly solidify them, you can grow single crystal, you can produce them by electrodeposition, by CVD, by PVD. Any technology, you make any alloy or any intermetallic compound, you can make quasi-periodic material. It's easy to make. People repeated my experiments a few days after the publication. They did the same. They had it. A few days. Easy. Are they made of rare elements? Maybe they are. Not at all. They are made of iron, aluminum, chromium, copper, titanium. Millions of tons of these elements are used every year. These are very abundant, cheap materials. So why is it that quasi-periodic materials were never discovered before 1982? Let me give you now my answer. And this is now becoming subjective. Number one, quasi-periodic had to be discovered by TEM, transmission electron microscope, because they were very small. And if you take SQ diffraction of a material which is quasi-periodic, instead of, it's polycrystalline, you have many little crystals, instead of points, you see rings. And you cannot see the 5-fold rotational symmetry. You lose the rotational symmetry. So it had to be done by TEM. So TEM is rule number one. You may say, okay, big deal. Why you? There are thousands upon thousands of people around the world who do electron microscopy. Why you? Well, let me tell you something. Yes, there are thousands upon thousands. Very few of them are truly electron microscopists. Most of them are students for higher degrees that work. They do transmission electron microscopy, but they do not become electron microscopists. Because to become an electron microscopist, you have to know the theory to the extent that you can teach it, and you have to spend hundreds of hours at the microscope until you become an expert in electron microscopy. There are very few experts in electron microscopy around the world. Not very many. I can tell you that in my department, I don't know how many, hundreds upon hundreds of students did electron microscopy, wrote their thesis on electron microscopy. You know how many electron microscopies we produced over the period of 40 years or so? 15. 15. And they're scattered all over the world doing electron microscopy. Very rare. And we are leaders in electron microscopy. So TM, number one. Okay, why you? Well, as I said, you have to be a professional. And my message to students, when I speak to students, okay, I recommend that you fix that contact one day, if you have the budget for it. They have the budget for it. Professionalism. My recommendation to you is the following. If you want to have a successful scientific career, you have to have mainly two features. Number one, broad knowledge of your field. You have to know something about everything in your field. That's not enough. You have to be an expert in one thing. Produce one peak of expertise, whatever you like. Something in microstructure, something in mechanical properties, optical properties, magnetic properties, electrical properties. Become an expert in something. Broad knowledge plus one expertise will make you a good scientist. Professionalism. But that's not enough. You have to have tenacity. Tenacity meaning be like a Rottweiler dog. You bite, go. Let me give you an example. There's one scientist in Belgium. I met him for the first time in my life a couple months ago. For the first time. I knew about him, and he knew, of course, about me. We never met. But here is his story. He saw quasi-periodic materials before me. He had the same diffraction pattern in his hand, his electron microscopy. He was a very good one. He came from a very good school in Belgium. And what did he do with his diffraction pattern? He filed it. And that was the end of that. His professor several years later, go through the files, take a slide and say, wow, this is Danny Shechtman's slide. Looks at the date, before 1982. So he calls his student. Dear student, how are you? Yes, professor, I'm fine, how are you? Say, says the professor, do you know that you saw Danny Shechtman's diffraction pattern before him? Said the student, of course, professor, of course I know. Why didn't you tell me? Says the student, you know, professor, if I told you, you would want me to stay for 2 more years on my PhD? I didn't want that. And we were very happy to meet each other. Tenacity. You find something interesting, don't let go. Sometimes, in most cases, it will be either an artifact or somebody discovered it 30 years before. But in some cases, just in some cases, you made a great discovery. Don't let go. And you have to believe in yourself. How can you believe in yourself? If you are a professional. You repeat your experiments, you convince yourself that you are correct, and then if somebody says, that's not so, tell him, repeat my experiment, or, if you're a theoretician, repeat my calculation and show me where I'm wrong. Saying it's not in the book is not good enough. So you have to believe in yourself. And resilience, I can tell you that I had a few ordeals. My promotions were delayed because Linus Pauling says that I am a quasi-scientist, and so on and so forth. I will not go into details on that. But, you know, you have to have some resilience and everything will be okay. And recently, in my last ordeal in Jerusalem, in the Knesset, I proved that I have resilience. And this was by far more harsh than my, than my battle with the scientific community. OK, just a few pictures, a nice picture, and that will be the end. These are quasi-periodic crystals in aluminum manganese. This is exactly the alloy in which I made a discovery, but this is scanning electron microscope. So here, these are crystals. You see 5-fold rotation symmetry, 5 here, see? And if you cut it here, you see the 2-fold, and you see 3-fold right here. Beautiful. And this was painted artificially by my friend Anpeng Tsai. He's in Japan, and he painted it to look like the cherry blossom, so that they like so much in Japan. And this is me. This is my number 10 grandson, future microscopist. Thank you very much.